Hello, my name is Saam Kaviani and I will be presenting this paper with the title of Evolutionary Design Building Skins with Embedded Biomimetic Adaptation Lessons. First, I want to focus on the importance of facades in playing an important role in terms of controlling of energy waste, and also I want to mention that majority of the existing facades are non-adaptive and that results in wasting large amounts of energy in order to maintain the internal comfort. And unlike the existing facades, living organisms, they tend to respond to the surrounding environment by adjusting themselves to the varying weather conditions. And an adaptive architectural envelope is required in order to improve the energy performance of the buildings. And this project is also inspired by biological adaptation lessons and living organisms in order to produce an adaptive envelope. The aim of this project is to study how biological processes, specifically natural science, can produce adaptation lessons, and through those adaptation lessons we want to see how the thermal and visual comfort of the occupants can be improved by producing this skin design methodology. Here we can see the decarbonization scenarios of the European Union for 2030-2050, and they focus on the emissions, the greenhouse emissions produced by cities, specifically buildings, that they play an important role in producing these greenhouse gases. And there are recommendations in European Union Commission reports, and some of them are focusing on programs regarding installation of energy efficient technologies, specifically on building skins and facades. There are some studies regarding the innovative skin designs, and in this project particularly we want to focus on the AUBEA towers specifically, and also in order to be focused we want to only consider the shading and visibility performance of the AUBEA tower and the proposed building skin for that on this paper. And the rest of the performance analysis will be further studies after this paper. In this slide we can see the requirements of users for sun shading systems, but in this particular paper we just want to be focused on thermal and visual comfort. There are so many ways to define thermal and visual comfort, and in this paper we want to define visual comfort by targeting the glare protection and also the visual contact to the exterior. And for thermal comfort we want to only be focused on minimizing the solar gains, specifically in summer, because the less solar gain is observed by the building, the less cooling system will be used to regulate the temperature. The methodology of this paper started by producing a mind map that in this mind map you can choose a climate, and based on that climate you can choose a living organism and see how that adapts to that climate, and inspire from that and see how these processes can be applied in architecture. And I will be walking you through some of the examples of the adaptation lessons that were extracted from this mind map. One of them is jackrabbit, which the inspiration from this animal is surface to volume ratio. Another one is ribbed cacti, which produces self-shading attributes. Another one is the granium plants, and also the stems of those plants, and they are fantastic in producing different groups for different functions and partitioning technique. Another extraction from that mind map was homeostasis, which is a tendency towards a relatively stable equilibrium between interdependent elements. And in the next slide, you can see the positive and negative feedback loop, and homeostasis works on the negative feedback loop, which recognizes changes and brings it back to normal. One of the examples of homeostasis in our daily life is how our body reacts when the temperature rises and we start sweating, which you can see on the left hand side, and also how the body reacts when there is an increase of glucose level in our body, that we can see how the negative feedback loop of homeostasis works in order to bring back the blood glucose level to the normal. The case study for this research is called the AUBEA Tower, which is located in Abu Dhabi in UAE, and has a unique kinetic facade system which is made of 1,000 individual shading devices. And I want to say that the biological principles in this study, based on Philip Stedman's statement, which is the idea of nature as a formal metaphor, has evolved into a collection of interconnected dynamic processes that can be implemented to improve the built environment and architecture, is applied into design. But the bridge between the biological processes and the design is computation, which acts as a bridge in order to implement and simulate those principles in order to bring that into architecture. And here we can see the details of each sector in this research, which you can see those principles extracted from the organisms in the mind map is in the biological processes category. And in order to apply that into the architectural design sector, we need to create a generative design platform, and also we need to simulate those principles by producing algorithms, and which can be taken into architecture. And here we can see how the negative feedback loop of this research works by selecting the type of the skin and applying the biological principles and taking that to the evolution process, and the selection sector, which is named as effector, which repeats itself until the best solution is detected. As this research has two objectives in order to optimize the facade, which was thermal comfort and visual comfort, we have to use the NSA-G2 algorithm, which is a standard evolutionary algorithm for multi-objective optimization purposes, and it stands for non-dominated sorting genetic algorithm. Here we can see the modified version of the algorithm, that we can also see that how the homeostasis mechanism has been applied, which works by detecting changes and inserting the morphological attributes that are extracted from the nature in order to regulate the system until the optimum visual and thermal comfort is achieved. In order to do the radiation analysis for this research, we used Ladybug plugin of Grasshopper, which it produces the accurate sound path of any given location, which was Abu Dhabi for our case study, which is AUBEA Tower. And on the right hand side, we can see that there are small seed points that are produced over the sphere, which is just an example that these seed points represent a radiation intensity. And this is just an example, and in the next slides we can see how that's applied into the AUBEA Tower. This slide represents how the view analysis works in this study, which is through the eye level of the occupants and the vectors that projected outside, which can be detected if there's an obstacle. Another representation of the applicability on the AUBEA towers. And on this slide, we can see that how those elements extracted from nature is applied into the geometries, which later on can reflect on the radiation performance and the view performance by controlling any of these elements. And here we can see the applicability of the homeostasis principles in the algorithm that is produced for this research, which there are two mechanisms that can detect the radiation intensity of 3.5 kilowatt-hour per square meter and also 4 kilowatt-hour per square meter, which that has been put as a set point in order to activate these homeostasis principles in order to regulate the temperature, the radiation intensity applied in the building. And here we can see the results of the applicability of the biological principles in the architectural skin, which you can see the development process of the geometrical shapes and the cells in the skin. On the left hand side of this slide, you can see the original AUBEA tower, and on the right hand side you can see the developed and evolved skin, which this shape, I need to emphasize that this shape is just an example, and this method can also be applied in different geometrical shapes. And applicability of the radiation analysis, here we can see the original performance of the AUBEA tower skin, and this is the evolved skin, which you can see the improvements in terms of reducing the excessive radiation, which was 1.7%, which was reduced to 0.5%. And here we can see the view analysis comparison. On the left hand side we can see the original skin, which the view was blocked for 56%, which was improved to 35% on the right hand side for the evolved and new skin. And lastly, thank you very much for your time and attention.